Thanks for having me. So yeah, today it's quite a difficult talk to follow because it's so broad and ambitious, and mine is going to be very concrete and about a specific problem. But maybe if there's one theme, it's a little bit taking certain cultural habits of the machine learning community and thinking why they worked and maybe perhaps applying them a bit more to causal problems. And so the project I'm going to talk about is called Adjustment Identification Distance, with the second title, A Gadget for Causal Structure Learning, where gadget is my co-author's idea. As a machine learning professor, he likes funny names. I like to avoid them, but now I'm working with him. So that's Sebastian Weichwald. And so because it's a bit of a more general audience, and even though Jack came before me and did a good job, I will still try to give a little bit of a short introduction into causality and particularly causal graphical models and the way I like to think about them. And I don't want to go too much to the philosophy. I'm not saying this is the right way of thinking about them, but this is my way of thinking about them. And the way I would like to illustrate this is a very concrete problem that I've worked with in my research. The only applied project I've ever done. I've tried to stay away from them. And it's about a problem where the sleeping lab at the University of Zurich approached us at ETH during my PhD. And what they were specifically interested in is that they want to understand better how sleep works. And sleep is apparently a very complicated process. And at the time, they joked to me that the only reason we know why we sleep is because if we don't, we die. And sleep is also very difficult to get a grab on because it's very multifactorial and there's lots of things going on simultaneously. But one thing we know quite well about sleep is that caffeine affects it. Specifically, we even know how, which is there's these different regulatory systems based on different hormones. One of them, and caffeine interferes with one of them. And so if you know something affects sleep, understanding how that happens gives you better insights into how sleep functions itself, right? So they approached us, and their question was, what is the causal effect of caffeine on sleep? Specifically, if we stopped drinking coffee, or if we drank more coffee, how would that change your objective measures of sleep? Your sleep length, your sleep depths, and all these complex ways we can measure sleep. And this is actually a remarkably difficult question for two reasons. The first one is they had data, actually quite good data, where people had been asked to come into they had been asked to come in, they asked to fill out a dietary form, so we kind of knew what they consume, and then they could go home with an EEG on them, so we have objective data. But the problem here is that you ask people to participate in the study, so it's not a controlled study. And that means that, as Jack raised the point, the two groups, in this case the groups of coffee drinkers and non-coffee drinkers, they differ at baseline in terms of other properties of theirs. So in this specific age, for example, we know that age has an effect on caffeine consumption, meaning older people generally consume more than younger people. And we also know that age has an effect on your sleep, but specifically we sleep less as we age. So in other words, it's very clear how to draw causal conclusions from this. We could very quickly fit a statistical model, very well predict how long people sleep based on their characteristics, but this could be entirely to these spurious correlations due to these other factors. Okay? And now I think Jack raised the point that this is a problem fundamentally about you're interested in a distribution you didn't observe. Specifically, we would like to know something about a distribution where we take control of coffee, because we would make a recommendation, we would tell people not to drink coffee, we would tell people to drink more coffee. And in this new distribution, this effect of these unobserved confounders, in this case age, or observed confounders, it is observed on coffee, would be gone. And in the real data we observe, this effect is there. So we have a transfer learning problem. We learn about something, one observation, we would like to learn something about another. We have statistics, which is very good at learning about observations. So very good at the first problem, it's very unclear how to use it to solve the second problem. Now the first solution we have to this problem is, well, if we want to learn something about a distribution that we didn't observe, how about we go around and try to observe it? So that's the idea of a randomized control trial. In a randomized control trial, you take control of the treatment, in this case coffee consumption. I would tell you, drink coffee. I'd tell you, don't drink coffee. I would randomly assign it, and that means that within this group, there is nothing causing coffee, right? The coffee is truly random, the coffee consumption. But in this case, we have a concrete problem here, which is we were not interested in the acute effect of caffeine. We were interested in the long-term effect. What does that mean? We know that if we get people, tell them not to drink coffee, and after 2 weeks get them to a lab, and we make them drink coffee, they sleep very badly. So we have done those trials. But we also know that in animal trials, if we have animals and we do heavy interventional effects on their sleep mechanisms, so for example, we could completely knock out their receptors for certain hormones, after a few months, they go back to sleeping normally. So there's a real reasons to believe that there is a difference between the habitual consumption of caffeine and its effect on sleep and the short-term effects. So that means we're interested in habitual consumption of caffeine. And there's nothing we can do there in terms of a trial because people don't adhere to trial. You can't really tell people to drink a coffee a day for the rest of their lives. They're not going to do it. It's very expensive. So in this case, we can't randomize treatments. Then there is a follow-up solution. And that follow-up solution is something Jack didn't talk about, but it's kind of the first naive solution, which is if your underlying problem is that your two groups, coffee drinkers and non-coffee drinkers, differ in terms of their covariates at baseline. Well, what if you cut both of these groups into subgroups where you fix these characteristics? So basically, instead of comparing coffee drinkers to non-coffee drinkers using our statistical tools, how about we compare old coffee drinkers to old non-coffee drinkers and young coffee drinkers to young non-coffee drinkers, and then we combine these estimates, and then what we kind of did in each of these subgroups, your treatment is as if random, because we fixed all the characteristics determining your treatment. And this is known as adjusting for the causes of the treatment. So in this specific case here, and now my little introduction comes to an end, this is obviously not possible because, for example, we assume that things like stress have an effect both on sleep and coffee consumption. It's very hard to quantify stress. It's very hard to measure stress. So it's not really realistic. So what we mostly did in this approach is we used the instrumental variable approach Jack talked about, combined with a little bit of other things like matching. And what we found is that there's some evidence that caffeine consumption does reduce your total sleep time. It's not very strong. I don't think these tools allow you to make strong conclusions, but there is a little bit of evidence there. Interestingly, aside from that, apparently all we found about coffee is that even though it's very addictive and has very strong withdrawal symptoms, all its other effects are positive, which I didn't know before this trial, this paper. But anyway, so the grand story I'm trying to tell is you can think of one way of thinking about causality, is that in traditional statistics, we have observational data, and we're trying to learn something about this data by modeling its distribution, and that allows us to, for example, among other tasks, predict very well given new data from the same distribution, make better predictive statements, right? And in causality, what we're usually interested implicitly is in experimental data that we unfortunately cannot generate, or sometimes we can, that's too strong. And then in this experimental data, we have what I'll call post-interventional distributions, so these new distributions. And then if we were able to observe them, we can draw causal conclusions because we actually observed what would happen in an experiment. And the promise of this causality as a whole, but also causal graphs in specific, is that under some circumstances, you can kind of sneak across here. For example, if you know exactly the treatments of your cause, you can use observational data and you can still use it to draw causal conclusions. But in order to be able to do that, you need this qualitative causal information. You need to know something about your system. With the IV case, you need to know these three assumptions hold. So there's always some knowledge you require. And the one elegant way of encoding that is with these causal graphs. Okay? So now what is this project actually about? Now that we've motivated why we care about this causal graphs, it's about, so what we know in machine learning is that there can be extremely hard problems that we for a long time don't believe we can do very well, like very high dimensional prediction. And then at some point, we get good benchmarks in place, and we get clear performance metrics, and then we throw enormous man hours at it. And somehow, through the ingenuity of PhD students mostly, I think, we are able to tackle these remarkably hard problems and develop things like neural networks, which broke all the rules of traditional statistics and nonetheless outperformed them. Okay? So that means that one very important thing in this new era of research is that we need to have a very good understanding of what it means to do well and what it means to do badly. Okay? And so what we are asking ourselves here is how do you so people have been working on this problem, which is an extremely hard problem, which is how do you learn the relations between a set of covariates? One of the sub-problems here is causal graphs, but there are some other ones, such as covariate clustering or causal representation learning. And all of them now have a new immediate follow-up problem, which is this very complicated object that's kind of combinatorial. It lives in this weird space with weird constraints, like a DAG having the acyclicity. And now we want to figure out how do we quantify uncertainty in this new space? How do we measure performance in this new space? And all the standard tools we have, all the losses we've learned very well in the reals, they kind of go out of the window. We have a whole new class of problems. Okay? So this is what essentially this project is about, which is how do we benchmark structural learners? How do we talk about distances and performance in these weird spaces where we're learning graphs? Okay, so I think I'm talking for a while. So the idea now is, so I'll probably try to go a bit faster here because it is a more applied audience than I thought. But so the object we're going to focus on, I now kind of explained them intuitively, but formally speaking, you can think of them as you have this graph, this directed acyclic graph. The acyclicity is sometimes criticized, but a common assumption. And in this graph, it encodes this causal relationship, which is what causes what are these direct causes. But more abstractly, you can think of it as encoding a density, specifically a factorization of your density. So it somehow encodes these conditional independence statements in your underlying system that allow you to more simply describe this density. But what's even more important, it also tells you how your system would behave under these manipulations. So this causal graph it goes beyond a traditional statistical model, which tells you something about how your distribution behaves. It also tells you, if you did these hypothetical experiments, denoted by this 2t, how would these new distributions behave. So in a more concrete case, what it's essentially saying is, if you have a very simple problem, is that this encodes some conditional independence constraint. In this specific case here, your joint distribution factor is like this, which is almost the trivial factorization thanks to base, with one extra step, which is there's no x1 in this conditional here. And that implicitly encodes that x1 is independent of x3 given x2. But what's even more important is that it tells you that this factorization, there's lots of factorizations that encode this, in this specific case 3, but it also tells you that this is the causal factorization. So if I manipulate the system, so if I did an intervention on x1, a hypothetical experiment where I take control of my coffee consumption and I force everybody to drink coffee, or I ban everybody from drinking coffee, then my new distribution is going to have this new factorization. So now we have a mathematical language connecting these many interventional distributions that we would really like to study to observational distribution. And now we can do this very odd class of problems that I think sometimes is underappreciated, but I think Yin Tian actually worked a lot on, which is called identification. So you can kind of forget about the data. You can just assume you've got the graph. And now you have a whole new type of problem, which is what you want to write down as what I call a functional in the observational distribution. And I think the more concrete way you can think about it is, I don't need to know, if I just know abstractly something about my causal system, what causes what are the steps I should take as a practitioner to estimate my causal effect? So what data should I collect? How should I collect it? What estimator should I use? So all of this is doesn't depend on the data yet, right? You could set rules for how to do it before you even looked at your data. And this is what you can kind of think of as a functional. It's an abstract rule for how to do your data analysis. And in this specific case, it's an abstract rule that connects your target do intervention to some quantity that in your observational data that you could actually compute if you then go out into the world and collect data. And there are three of them that I will focus on. One of them, which I think is not talked about, but it's actually very powerful, is the claim that there is no causal effect. And what a no causal effect claim essentially corresponds to in this weird world, where you think everything about as these abstract densities, is that you're saying that your density of your outcome, if you did an experiment on your treatment, is just the original density again, right? So if I make people drink coffee, their sleep will not change at all. There's no change here. And another important one is that sometimes we don't have enough causal information to find such a functional, actually in practice almost always. And in this case, we call it not identifiable. And now the thing that mathematicians like is we've created a language, we've created a world where we can now answer all these questions with mathematical rigor, assuming we have this causal graph. Very removed from reality, but we can do it. I think Yin, did you actually work on the ID algorithm? Okay, so this is a very remarkable algorithm that can kind of solve this question of quite a bit of generality in a specific setting. Okay, so now we have this object. It kind of allows us to make concrete decisions in an applied setting, or at least it promises to give us the ability to do that. But you would say, well, but I will never know it, right? I never know the causal graph. And that is true, and I think it is still true to this day, but there is a lot of research on how we can learn them as well. Specifically, they do encode certain pieces of information that are also present in your observational data. So for example, I've explained that DAGs, yes, they say something about these causal distributions, which you don't observe, but they also encode conditional independence statements in the original distribution, and that we're good at, right? We can test conditional independencies. So you can learn these causal graphs up to some extent. That's called causal discovery. And there's lots of ways to do it, and all of them have in common, I think, that they don't really work that well yet in practice, but they give us important insights into how this extremely hard problem is feasible. And there's also an important sub-point here, which is what we noticed here is that a lot of times we can only learn the DAG up to a certain amount of accuracy. And that means we have lots of graph types to accommodate this. So you're now starting to kind of get a picture, right? You have this very complex world with these abstract tasks, solutions from these graphs. There's lots of types of graphs, lots of decisions happening. And so there's a lot of unclarity. And so now you might ask yourself, well, these causal discovery algorithms, obviously they need to get published. So they need to do a simulation study. They need to show they work. How do they measure that they work? And the remarkable thing here is you will find that there's kind of a contrast between the complexity of what they're trying to achieve and then how they actually benchmark it. Because the way they benchmark it is you have this complex object, you've given it lots of meaning, and then they kind of forget about it. And they treat it again as if it was just a 0-1 bit encoding and compute what's called the structural Hamming distance. So the Hamming distance is a distance between two bits of information. It just counts zeros and ones and whether they match or not. And they do exactly that with the graphs, so they used to. So for example, if you had two graphs like this, you literally just go there, you treat these as 0-1 encodings. 1 means an edge is there, 0 means it's not there. And then you go through your graph and you actually encode each edge twice, right? So in one direction and the other direction as a matrix. And then you count the number of mistakes. So in this case here, for example, if you, let's say you learned this, you think this is the true graph, somebody tells you, no, it was this after all, you want to figure out how well did I do, then they would say you made 2 mistakes. One, because here the causal effect goes from x1 to x2, and here it goes from x2 to x1. And one here, there is no causal effect, and you told me there was a causal effect. And so it's kind of underwhelming a bit, because you suddenly throw away all of this, what you want to do with the graph, right? And there's also ambiguity here, because the moment you have these very complex graph objects, there's lots of edges. And so the question is, do you keep treating them as just 0-1 mistakes? Do you start giving them weights? People say structural Hamming distance. Sometimes they mean different versions of it. So there's some cases where you would double count this mistake. So you would count this mistake as 2 and this mistake as 1. So there's a lot of ambiguity. And there's a more profound insight, which is a subtlety to DAGs, and I don't want to overemphasize it, but I think it makes a point, which is, so suppose you're actually learning a DAG. Then you have this very odd behavior, which is if you, identifying functional is an equation and that's true for all your models, right? And your causal DAGs, the more edges they have, the more models they are able to describe. In a causal DAG, the information is in the missing edges, not in the edges that are there, okay? So if you add an edge, you kind of just increase your model class. So a graph that has no edge just means there's no causal relation between anything. And then the moment you add an edge between x and y, you're saying this is the class of all models where there's a causal relation from x to y. But that includes the models where there's no relationship, because that just corresponds to a 0 effect. So you have this weird characteristic, which you could very easily prove is basically trivial, which is that if you were learning DAGs and your target is to do identification, then learning too many edges never hurts you. Because you will never make a mistake for thinking there is an extra error there, as long as what you've just now learned is a superset of your true graph. Another way to think about it is in a DAG setting, and it's very specific, if you know the causal ordering, you can identify every causal effect, okay? So what that also means is that the structural Hamming distance, it ignores the nature of your mistakes. And in this specific case, what we see is that there's an asymmetry to the mistakes you care about. So if you wanted to learn a DAG, you care a lot about missing edges, but you don't care so much about having a few edges too many, okay? And this is specific to the problem we're trying to do, which is identification. If we did a different problem, this behavior could be reversed. But the point is just that because we ignored the problem we're trying to solve, we kind of missed this extra bit of, like, it's almost leeway, right? We don't have to be quite as good as we thought we would. So maybe we shouldn't penalize our algorithms for being bad at doing this, okay? And so the idea of this project was essentially just to recenter this, to take a step back and say, well, what are we using these graphs for? And more broadly, what are we using structural learning for? And say that's what we call a task-oriented perspective. So instead of saying, do these 0-1 bit encodings, computing these structural Hamming distances, what if we benchmark just by asking the following question, which is, how well are we off for some task using a structure S-guess to perform the task we intend to use it for if the ground truth was in fact S-true? So in other words, suppose we learned this S-guess structure, then somebody tells us, oh, by the way, the whole time S-true was the real structure, and we did whatever we wanted to do with it. Would we have messed up or would we not have messed up, okay? And more specifically, because we wanted to just focus on the causal graphs, here we will focus on a specific task, which is how well would we do if we wanted to identify causal effects. Okay. So you can summarize this as just essentially now you have a class of distances, and to specify this class of distances, what you need is you need three choices. You need to choose a range, which is kind of the inputs for your task you're interested in. So if your inputs are learning causal effects, it's just treatments and outcomes. Then the second thing you need is what we call a task solver, which is an algorithm that, given abstract inputs, tells you a procedure for how you would tackle that task. So given X and Y, give me an identification formula, which I think is essentially the idea of the ID algorithm, right? This is by definition a task solver. It tries to abstract away the human agency and force you to do it very concretely, ahead of time what you will do. And then finally, and that is technically not a choice that's specific to the task, you then need another algorithm, which we call a verifier, which is able to assess whether your decision that you made would have been correct if your true model comes from another class of models defined by you as true. Okay? And this is another important insight in my opinion. If you actually take a step back and you think about the structural Hamming distance again, you can actually see that the structural Hamming distance is a specific case of a task-oriented distance for one specific task, which is deduce parent-child relations. Specifically, you can think of the structural Hamming distance as what is your range here? Well, you go about over all the ordered pairs, so you don't double count them. One choice would be to double count them. So you go once over all the x's, then all the x's, then all the y's, all the t's. So 2 times 2, but you cut off the upper half. Doesn't matter so much. And then for each of them, your solver produces 3 types of output. It either says, okay, I believe that y is a parent of t, or it says I believe y is a child of t, or I believe there is no relationship between the 3. And then we need to verify this, and because this is a very concrete task where there's not much of choice, this is very easy here, which is you just go into your other object and you say, well, I was just given a claim. Is this claim correct? Is in fact I was told that y is a parent of t. Is it in fact a parent? And if it's not, then you say there's a mistake. Okay. So going back to thinking why do we use the structural Hamming distance, now that also raises the question, well, when you use it, you're implicitly saying what I really care about in a graph is the parent-child relationships. And I think if we take a step back and ask ourselves what we do with causal graphs, this is rarely what we really do. So there's already a very simple insight here, which is we could, for example, just replace this with ancestors' descendants, and then we would just be asking, is there any causal relationship? Is there any treatment effect we expect? And I think there's lots of applications where this would be more natural. Now we wanted to do this for the identification, so it's basically the exact same idea, and all we need to do now is think about these identification strategies, right? Of which this ID algorithm is, I think, the only natural candidate at first. But so what we did instead is we took this old paper from 2015 that had kind of sketched a lot of these ideas, and what they said is, remember, when you have a DAG, you can always adjust for the causes of the treatment if you observe them. So then you can turn that into a strategy, and we call this the parental adjustment strategy. So what we do here is giving this g, this t, and this y. This is the inputs, the treatment outcome, and the graph you believe is true. We have 2 types of strategies. We either see that y is a parent of your treatment. In this case, we say is not a parent. In this case, we adjust for the cause of the treatment. So this is very abstract, but really in the real world, that would just mean we would do this trick that I explained with the coffee, which is we cut our treatment groups into these little subgroups and do our analysis there. And if it is a parent, well then, if something is a direct cause of something else, a cyclicity, that means there is no effect. So in this other case, we say there is no effect and return fy. But the important insight now is that once you think about it this abstractly, and you realize that every identification strategy corresponds to a distance, you realize, well, there's lots and lots of identification strategies. This is just an arbitrary choice. And so this paper, Peters and Bloom in 2015, they kind of just sketched one idea, and we really need to live with this ambiguity. There is no one way to use a graph. There's lots of choices. One way to do it would be, for example, to use the ID algorithm, but then we have a problem, and that is a very practical problem. So if we actually now want to define a distance, we have 2 concerns. The first one is, do we think this really reflects what people do with our graphs? Okay. So in this case, I think the parent adjustment distance would tick a lot of boxes, because I do think some people do use it. They do adjust for the cause of the treatment. And then there's a second concern, which is an interesting insight which I never realized before this project. But do we have a verifier? In other words, do we have this other algorithm that tells us, that what we did is correct?
Here's a question.
Yeah.
Is this model in some sense Markovian?
Yes, so the original distribution is a Bayesian network, so it satisfies a Markov property, and these dual interventions are sometimes called causal Markov properties. Yeah. So this verifier question, so for example, now with the ID algorithm, we don't have a verifier because it's not a research problem. Nobody ever thought about verification as a natural problem, even though from a computer science perspective, that's almost always the two problems. Given a task, how can you solve it? Given a candidate solution, can you check whether it's correct? But for historical reasons, nobody ever thinks about the verification. So in this concrete project, that meant we don't really have much of a choice. We need to kind of focus on this verification problem, which is the sound and complete algorithm that takes a candidate identification formula and tells us whether it's correct or not for our new graph G. And there's no research, so the only thing we can do is we can use what's called sound and complete identification criteria. So for some classes of identification strategies, like adjustment, people studied them so deeply that they found sound and complete criteria. And then a sound and complete criterion is implicitly a verifier. So nobody studies verification, but if you study identification deeply enough, a verification result pops out. And so what does that mean in this concrete case here? Well, we have 4, let's call it verifiable classes of identification formulas. The first one is the no effect one. So if somebody tells me, oh, there's no effect in this graph, well, I know that this is only true for all models if there is in fact no causal path. This is descendant, just means there's a directed path from my t to my y, okay? So that one's, I think, quite intuitive. For these other ones, it's a little bit less intuitive, but there's also, people study them so deeply because they're such natural strategies that they found solutions. So for example, the adjustment criterion answers you exactly when this formula is true for a graph. Not identifiability is not always answered. I think the ID algorithm would actually be a general verifier for that one, but we focused on CPDEX, where you can check it with this criterion called amenability. And then I've worked a bit on instrumental variables to also find a sound and complete criterion. But other than that, I would go as far as to say that there are no verifier. There's no verifier research, and there's no other sound and complete identification strategies. So these are the 4 tools we can use, nothing else. And so what we did is we just focused. We didn't want to play too deeply around it, so we just proposed 2 other distances with the main pitch just being there's lots of choices, so there's no ground truth. We need to debate as a community what are the right choices, which is we just tweaked a little bit these adjustment sets. And we also tweaked a little bit how we deal with the no effect case, which is in the parent adjustment distance, we only say no effect under very strict conditions, which is if your outcome is a parent of your treatment. So if it's the reverse situation, it's a direct cause. So if 2 nodes are very far away from each other and have no causal relationship in the graph, we will still try to check whether there is really no effect. And here we go a completely different way. We just say we only bother to go into the identification if we see that there is a direct path from your treatment to your y, which means y is a descendant of t. In all other settings, we just say, okay, well, there's no effect according to my graph. And so now we have 3 distances. And so now we need to establish that that matters. All this debate about tasks and choices and ambiguity. So what we did then is we did a little study where we took heterogeneous graphs and we just removed 1 edge. All we did is remove 1 edge. So you're very close to the truth. You're almost there. And then we computed our distances. And so you know the structural Hamming distance in this case is always 1. You're right next to you is truth. And what we see with our adjustment identification distances with these 3 different strategies is that they are correlated, yes, but they show very different behaviors. And particularly the parent distance immediately jumps up to be quite large. And I think it's because of this slightly weird choice of saying, even if there is no path from from y to t or t to y, I will always try to estimate this effect and not just say, oh, it's just an observational effect. I believe there's no effect. They're very conservative. They don't want to say there's no effect. And I think that leads to lots and lots of mistakes if you just add a single edge, remove a single edge. And we also computed the correlation. And so again, what we see is that there is very little correlation, especially to the parent distance, whereas the ancestor and OSA distance are much more correlated. And they also measure, the one distance is very steep, close to your solution, the other one's not. But the most important insight is these choices, there is ambiguity here, ambiguity. So there's choices to be made, and these choices matter. And they will impact how you will benchmark your discovery algorithm. OK, so now I have, I still have 10 minutes, actually. OK. The last thing I wanted to talk about, so we've had 2 insights, right? The first insight is we need to work more on benchmarking. We need to establish what does good performance mean in causal discovery. And there's lots of ambiguity here, lots of choices, and we need to maybe have a clearer debate about them, because identification is not like deciding parent-child relationships where there's only one strategy to solve it. There's lots of ways to solve this problem, and that means there's lots of choices. The other insight was study verification. Nobody studied it for some reason. I think it'll give us more insights into causality if we did study it as well. And now the third thing I want to discuss, and this is another machine learning thing, is machine learners are very good, I think, to use primitives, to kind of solve certain problems really well, linear algebra problems, and then just trust them and run with them. And I think the causality community could work a bit harder on being cleaner on the algorithmic side. And so the problem I want to raise here is now we want to compute all these distances very fast. And what we see here is there's there's a bunch of problems we need to solve. All of them are actually, they look a bit difficult, but what we'll show now is that all of them are quite easy. Specifically at first, if we want to compute these distances, we need to compute all these sets: parents, descendants, ancestors, optimal set. And for the descendants, maybe you're aware of this, I don't know, but there's this very common problem, super standard problem in theoretical computer science, which is called reachability, which is starting from, you have a directed graph, starting from a set of nodes, walk down the directed paths and record all the nodes you can reach. That's why it's called reachability. And these three things up here are just special cases of reachability. But these other problems we need to solve here, including this amenability condition and this value adjustment criterion, they're not immediately obviously reach problems. And my pitch now is I'm saying if you think about it the right way, almost all problems in causality that you run into, algorithmic problems, they are special versions of reach problems. So to illustrate this, let's go quickly over the problem of amenability. So amenability is you have a graph now where not every edge is directed. So some of them are undirected. This encodes you're not sure which direction the causal effect is. And you want to estimate the causal effect on, let's say, x1 and x3. So some undirected edges don't hurt you because, for example, here you know that still, even though this edge might be pointing this way or that way, you know that x1 is never a descendant of x3 or vice versa. Sorry, x3 is never a descendant of x1, so you know there is no causal effect. So even though you have missing information, you can make a decision about your identification strategy. Whereas if this edge is missing over here, then you have a problem because you can't decide whether this is a confounder, a measured confounder, or a mediator. And depending on what it is, you either need to adjust for it or you're not allowed to adjust for it. Okay? So reachability is equivalent to saying all possibly directed paths from T to Y start with a directed edge out of T. What does that mean? All these paths where you have a mix of undirected edges and directed edges pointing from your treatment to your outcome, they're not allowed to start with an edge of this form because then you have ambiguity. And the idea now is this is very close to reachability, right? You're walking down paths and you're storing which nodes you reach, but you have one annoying thing, which is the first step is a little bit different because in the first step it matters. You're only supposed to start walking if it's an undirected edge, okay? And the idea, and this is a follow-up project, it's not actually in this paper here, but we're working on it right now, is what you can do is you can kind of create this new graph, we call it a task-specific graph, where you duplicate your original set. And then you add these directed edges according to certain rules that determine you want to study these possibly directed paths in your original graph. So you build a new graph where the directed edges in this graph encode whether the original graph you were looking for exists. And the way you encode these directed edges in this new graph is via this thing we call a rule table, which just tells you when is there an edge between two nodes in your new graph. Okay? So you have this very compact description of it. And intuitively what this is really saying is given some causal algorithmic problem, which gives you a G and some sets L that kind of specify I care about the possibly directed paths from X, or I care about D separation from X given Z, then we map it to this new graph. In there, everything becomes a reach problem, and then all I need to do is map our solution back. And with this way, if I do this problem really, really well, and I make it easy to specify these two things, I can reduce lots of causal problems into one single, very well understood algorithmic primitive, reachability. And what we're saying is that for all these little problems, if you think carefully about these rules, you can solve them. So for example, the D separation table, which maybe some of you know about, it's a bit of a complicated algorithm, baseball algorithm. I had to teach it. It's not so easy to teach it to students. If you think about it in this task-specific reachable problem, all you need to do is this rule table completely specifies how to solve this problem as a standard reachability problem. And then in the real practice, you don't even have to create this graph. It's just a tool. It's just a tool to understand how your algorithm works. But you have a linear time, I guarantee. OK, and so what we saw here is that almost everything in causality is about walks and whether they exist. So it's very amenable to this problem. So all of these problems here, they're all solvable in linear time, except computing this optimal set, because it's a bit more complicated. So that one takes quadratic time or cubic time if there's lots of edges. The m is the number of edges, p is the number of nodes. Everything else works in linear time. So you can solve these very complicated distances where you have to go over all these t and y's in very low polynomial complexities, including if there's sparsity, they immediately drop, because reachability elegantly exploits sparsity. And so what we did, if we test this then in the real world, that means we can solve very problems that were previously quite difficult. So in this 2015 paper, they had these large graphs, 1,000 nodes, which I don't think are actually that large for practice now, where it took them 1 to 2 hours. I think specifically it was 2 hours, but on a new hardware it would be a bit faster. And we can do them in milliseconds, because once you can really focus on the good computer science side of the reachability, and these translations are elegant, then you can really exploit that this problem has been solved very well. And we don't have to rely on statisticians coding for speed, which they can't do. I can't do it, at least. I'm a statistician. Yeah, OK. So we've also, if anybody here works on causal discovery, we've tried to make it as easy as possible to access this. So it should be trivial to use. Please tell me if not, then we'll try to fix it. And I hope I've given you some thoughts about algorithms in causal discovery, well, algorithms in causality, benchmarking causal discovery, and verification. Thank you.
Thank you. Are there questions? Yeah.
Yeah, okay, thanks a lot for your talk. So the speed ups look very impressive. So I personally worked with SID quite a bit, so that's very cool to know. I have one question. It's a bit tangential, but regarding the initial example. So you mentioned long-term coffee and long-term sleep, right?
Oh, yes.
And so I presume that those are sort of aggregates over longer time horizons of two variables, potentially overlapping. So this makes me wonder, first, in this particular example, are we sure there's an acyclic graph connecting those two instances? And then on a broader level, is there something we could do for adjustment identification instance or distance or any of the other distances in a setting where the acyclicity assumption may be at least partially violated, such as potentially in the example?
So I think there's 3 questions in there. The first one is, yes, of course, there will be a cyclic effect. There's no reasons to believe that people who don't sleep badly don't try to medicate with coffee. There's almost certainly a cyclic effect. However, my understanding is, I haven't tried to figure the math out too deeply, is that instrumental variables also protect you against reverse causality to some extent. You seem more skeptical, but at least they say they do. I think that's what the original economics papers used them for, right? It was for price mechanisms where there was a cyclic effect between, I think, the price of milk and the price of butter. The second question was, how can we use the structural intervention distance or the concept of task-oriented distances in cyclic graph? And my answer is, it's completely flexible, right? All you need to do is you need to tell me what you want to do. And that, I think, is a very hard question that lots of people can't answer, but it's a very important question. Is what do you want to do with your graph? And then the second question is, if you want to do that, how would you try to abstract what you're trying to do into this abstract algorithm, which is this identification strategy? And then the third question, which is then for the theoreticians, can you falsify them? Can you verify them? And once you have these 3 ingredients in place, I don't really care about the graph anymore, right? It's more of a framework of creating distances than a specific. So
I could create my new distance potentially for specific use case of cyclic graphs.
Exactly. You need to sit down. You need to think, what do I want to do with them? If I want to do that, how do I do this abstractly as an algorithm? And then how do I check solutions from them? And then I'm not sure, because cyclic graphs might be a little bit more complicated, but I would not be surprised if you can use reachability-based algorithms to do it very fast as well, using our tables.
Quite interesting. Thank you.
Please.
Yeah, I had a question about reachability.
Yes.
I've looked a bit into the kind of causal network discovery literature recently, and I've started playing around with algorithms. And one algorithm I've used is this depth-first search algorithm to calculate a topological sorting of a graph. Yeah. And I just wondered, is reachability related to that sort of operation on a graph that sort of sets up whether you can, that's the sort of thing you do before to set up the graph, or the calculations in the right order to do the.
So reachability is the main way to solve reachability is depth-first search or breadth-first search. But depth-first search is kind of even more concrete than reachability. Reachability is, well, both. So breadth-first search and depth-first search are very concrete things you do in your implementation. and they can be used to solve reachability, but they can also be used to solve other problems whenever you have this queuing problems. Whereas reachability, and that's something we care about because we want that to be very clean, is if this very, very concrete problem of given a directed graph and a starting set of nodes, find all nodes I can reach by walking down directed paths. However, I am sure you can solve that problem with reachability. But the naive depth first search algorithm, which is already linear time, I don't think would do it.
Do you have to assume that the graph is directed acyclic to begin with, or
no? So it's not nothing to do with acyclicity, because it doesn't. You don't have to walk into these infinite. They might exist, these infinite loops, but you don't have to walk them to find all reachable nodes. So it's really just a directed graph. So that's also an important insight, that this graph we build, it happens to be directed, but it's not a DAG. In the example I gave you, unfortunately, I think it is a DAG, but usually it's not a DAG.
Any other questions? Yeah.
Thank you for the talk. It's maybe a naive question, but I was wondering if you consider that you can. So you are under no unmeasured confounding here. You suppose that you can measure everything.
Well, so we don't suppose anything. We were given. We know what people study, and we know that DAGs and CP-DAGs are kind of the starting thing. And so we looked at distances for DAGs and CP-DAGs. However, you're completely right that one thing you would want for your identification strategy is for it to be sound and complete, right? So when there is a solution, it should produce a solution. It should tell you when there's none. The moment you have unmeasured confounding, adjustment, these three tools we use, which is saying no, not identifiable, adjustment, or no effect, they aren't powerful enough anymore to give you a sound and complete strategy. So the moment you do that, you would need to go beyond that, start using IV, start using front door, start using the ID algorithm, but then you have the problem of verification, which would have gone beyond this paper, and I think is a very hard problem. My first intuition for it would be that it's probably NP hard, but that's why I think we should study it more deeply.
Okay, all right, last question.
So, very nice talk, thank you. Did you try out different causal discovery algorithm to see how they perform in, let's say, adjustment formula?
We did not. We were thinking about doing it at some point, but yeah, the difficulty there is obviously it's a very hard thing to set up well, right? There's lots of choices and they're a bit capricious, and we were in a bit of a crunch, so we didn't. But it's a very natural follow-up question, yes.
Okay. All right, let's thank the speaker again. Thank you.